Planetary science discovery explains Pluto's formation. Discover the kiss and capture mechanism that created the Pluto-Charon binary system, challenging theories on planetary formation and evolution. Billions of years ago, in the icy outskirts of the solar system, a dramatic collision forged the unusual pairing of Pluto and its moon, Charon. This celestial dance defied expectations, birthing a binary system where two icy bodies orbit a shared center of gravity. A new study from the University of Arizona challenges long-held assumptions about how these bodies formed, offering fresh insights into planetary evolution. For decades, scientists believed Charon formed through a massive collision similar to the one that created Earth's moon. In this scenario, two bodies collide, stretch like fluid, and eventually merge or eject debris that forms a moon. While this model works well for large, hot planets, it falls short when applied to the smaller, colder Pluto-Charon system. The new research highlights the importance of considering material strength in these icy collisions, revealing a kiss and capture mechanism that redefines our understanding of planetary formation. Pluto and Charon's unique characteristics make them the largest binary system in the trans-Neptunian region. Their shared orbital axis and comparable sizes, with Pluto's diameter about 1,200 kilometers and Charon's about 600 kilometers, suggest a linked history. Their wide, circular orbit also implies a formation scenario that preserves substantial angular momentum. Traditional models treated colliding bodies like fluid blobs, ignoring the strength of rock and ice. However, collisions involving smaller, colder objects, such as Pluto and Charon, occur at slower speeds and involve less mass than Earth's moon-forming impact. Adine Denton, a NASA postdoctoral fellow, spearheaded this study using advanced simulations to account for the actual structural strength of these materials. Denton explained, Pluto and Charon are smaller, colder, and primarily made of rock and ice. When we accounted for their material strength, we discovered something completely unexpected. Using simulations on a high-performance computing cluster, researchers found that during the collision, Pluto and Proto-Charon temporarily stuck together, forming a snowman-shaped object. This brief union allowed gravitational forces to stabilize Charon's orbit, evolving into the binary system seen today. This kiss and capture scenario differs significantly from the traditional hit and run or graze and merge models. Eric Ospaug, a co-author of the study, noted, the model parameters that work to capture Charon also place it in the correct orbit. You get two things right for the price of one. The collision's dynamics required precise conditions. Simulations showed that a grazing impact angle, around 50 to 70 degrees, was critical for Charon's capture. The relative collision velocity, approximately 1 km per second, needed to align with the mutual escape velocity of the colliding bodies. Additionally, the study modeled Pluto and Proto-Charon as differentiated objects with rocky cores and icy mantles, approximating their compositions as 85% rock and 15% ice by mass. The findings challenge earlier models suggesting extensive deformation and mixing during such impacts. Instead, this research shows that Pluto and Charon remained largely intact, preserving much of their original compositions. This intactness implies that Charon may be as ancient as Pluto. Furthermore, the collision deposited substantial internal heat into both bodies, potentially influencing Pluto's geological evolution and supporting theories of a subsurface ocean. This heat, generated through tidal friction as the bodies separated, may have sustained internal activity long after their formation. The implications extend beyond Pluto and Charon. Other binary systems in the trans-Neptunian region, such as Eris and Dysnomia or Orcus and Vanth, might have formed through similar processes. Binary systems common among large trans-Neptunian objects, yet their formation mechanisms remain debated. Traditional theories, like the streaming instability, where gas drag in the protoplanetary nebula aggregates small solids into larger bodies, fail to explain the largest binaries. The kiss and capture model may offer a broader framework for understanding these systems. Pluto's geological evolution offers further intrigue. The internal heat generated during its collision with Charon could have contributed to the formation of a subsurface ocean. Such oceans are believed to exist beneath icy shells on other solar system bodies, like Europa and Enceladus, but their persistence on smaller worlds like Pluto is less certain. Heat from tidal interactions might explain how Pluto retained enough thermal energy to support liquid water for extended periods. This discovery could reshape our understanding of habitability in the outer solar system, offering clues about where to search for extraterrestrial life. The collision also shaped the distinctive features observed on Pluto's surface. Geologic formations such as Sputnik Planitia, a vast nitrogen ice glacier, might have connections to the heat and dynamics introduced during the Charon forming event. These features suggest that Pluto experienced significant resurfacing, driven by internal processes fueled by the collision's aftermath. Studying these processes could reveal more about the interplay between external impacts and internal planetary activity. The discovery's implications for binary systems extend to their potential role in broader solar system formation theories. By analyzing how Charon's orbit evolved to its current state, researchers can refine models of planetary migration. This binary system, like others, acts as a natural laboratory for understanding angular momentum transfer, tidal dissipation, and orbital mechanics. The kiss and capture scenario provides a case study for how binary systems can form and remain stable over billions of years. The research team is already planning follow-up studies. Key questions include how tidal forces influenced the early evolution of Pluto and Charon when they were closer and how this scenario aligns with current geological features. Denton emphasized, "We're particularly interested in how this initial configuration affects Pluto's geological evolution. The heat from the impact and subsequent tidal forces likely played a crucial role in shaping the features we see on Pluto today." Published in Nature Geoscience, this study invites a re-evaluation of planetary formation models. By incorporating material strength into impact simulations, it provides a more nuanced understanding of how icy bodies in the outer solar system evolve. The kiss and capture scenario not only explains Charon's formation but also deepens our appreciation of the dynamic processes that shape planetary systems. Beyond Pluto and Charon, these findings could revolutionize our perspective on other icy bodies throughout the solar system. The techniques and insights developed in this study could apply to moons, asteroids, and other objects that bear the scars of ancient collisions. As researchers continue to refine their models, the kiss and capture mechanism may unlock answers to long-standing questions about the origins and evolution of celestial bodies across the cosmos. The Pluto-Charon system is one of the most intriguing features of the outer solar system. Their binary nature, with both bodies orbiting a shared center of gravity, is unusual and defies many of the conventional theories about moon formation. This pair, considered the largest binary system in the outer solar system, challenges our understanding of how celestial bodies in the cold, far-reaching parts of the solar system came to be. One of the primary reasons for the interest in Pluto and Charon's origins is the fact that their interaction contradicts most assumptions about how moons and planets form. The classical theory of planetary formation involves a catastrophic impact, such as the one believed to have formed Earth's moon. According to this idea, the impact between two celestial bodies ejects debris that can then form a moon. However, for small, cold bodies like Pluto and Charon, this process seems less likely. These objects, which are primarily composed of rock and ice, would not have experienced the same kinds of extreme temperatures and high-speed collisions found near warmer planets like Earth. In this context, scientists have turned to simulations and other modeling techniques to understand the Pluto-Charon system's origins more clearly. New models have proposed that the collision between Pluto and Proto-Charon was not as violent as the impact that created Earth's moon. Instead, the two bodies may have kissed rather than violently collided, gently merging before gravitational forces could stabilize their orbits. This slower, gentler interaction suggests that the moon-forming process on cold, small bodies involves different dynamics than what we see on larger, hotter planets. Another important element in understanding the Pluto-Charon system's formation is the role of material strength. Traditional models of planetary collisions often assume that, upon impact, colliding bodies would behave like fluids, deforming and mixing as they collided. But simulations that factor in the material strength of icy bodies reveal that Pluto and Charon likely collided at a lower velocity, about 1 km per second, than the higher velocity impacts seen on larger, more massive planets. The material properties of ice and rock, which make up Pluto and Charon, mean that these bodies would have been less likely to melt or deform significantly. Instead, they would have briefly stuck together, forming a temporary shape that allowed them to stabilize into the current binary orbit we observe today. Interestingly, this new approach also suggests that the Pluto-Charon system might have formed much earlier in the history of the solar system than was previously thought. The preservation of their original compositions implies that the two bodies could be as ancient as the early solar system itself. This challenges the prevailing theory that moons are typically formed from debris ejected during violent impacts and suggests a more complex process of moon formation in cold environments. One key aspect of the new model is its emphasis on the specific conditions that would have been necessary for Pluto and Proto-Charon to form their binary system. The simulations show that the collision had to occur at a grazing angle, between 50 and 70 degrees, for Charon to be captured into orbit around Pluto. Furthermore, The relative velocities during the collision had to align precisely with the escape velocity of the two bodies, ensuring that Charon was trapped in orbit rather than escaping into space. These precise conditions are crucial to understanding how binary systems like Pluto and Charon can form and remain stable over billions of years. The research also reveals that Pluto and Charon's formation didn't result in the kind of significant mixing or deformation that previous models had suggested. Instead, the icy bodies remained largely intact, preserving their distinct structures. This suggests that, unlike large planets where impacts lead to substantial mixing and differentiation, small icy bodies like Pluto and Charon retain much of their original composition after a collision. This discovery is not just limited to the Pluto-Charon system. The findings have broader implications for understanding other icy bodies in the outer solar system, particularly those in the Kuiper belt. These objects, similar to Pluto and Charon, are smaller and colder than the planets in the inner solar system. By studying their formation processes, scientists can better understand the conditions that lead to the creation of binary systems, as well as the long-term stability of these systems. The study also raises intriguing questions about the possibility of similar mechanisms occurring on other moons in the outer solar system. For example, other trans-Neptunian objects or moons of gas giants, such as Neptune's moon Triton, could have formed under similar circumstances. If the kiss and capture mechanism is applicable to other systems, it could lead to a rethinking of how moons and planets form in the colder, more distant regions of the solar system. This would significantly impact our models of planetary evolution and the dynamics of celestial bodies in these remote areas. Ultimately, this new research about Pluto and Charon's formation provides essential insights into the way small, icy bodies evolve in the outer reaches of the solar system. It suggests that the conditions for moon formation are more diverse than previously thought and that icy, small bodies may have a different history than the larger, more massive planets and moons closer to the Sun. Understanding this process may not only help scientists unravel the mysteries of Pluto and Charon, but also improve our understanding of the broader processes that govern the formation and evolution of moons and planets across the cosmos.